Problem 57 states a rubber ball bounces. We'd like to understand how the ball bounces. Part A says a rubber ball has been dropped and is bouncing off the floor. They want us to draw a motion diagram of the ball during the brief time interval that it's in contact with the floor. Show 4 or 5 frames as the ball compresses, then another 4 or 5 frames as it expands. What is the direction of the acceleration vector during each of these parts of the motion? Part B, they want us to draw a picture of the ball in contact with the floor and identify all the forces acting on the ball. Part C, we need to draw a free body diagram of the ball during its contact with the ground and identify any net forces acting on the ball and in what direction. And for D, they want us to write a paragraph describing what we learned from parts A to C. And we want to answer the question, how does a ball bounce? So the goal of this question is to understand how a ball bounces and what its acceleration is and the forces acting on it when it's touching the ground. So for the compression of the ball when it reaches the ground, I've drawn these frames here. Frame 1, I've drawn where the ball has just made contact with the floor. So it hasn't started compressing yet. Its velocity has not started to decrease. So it's got a constant velocity downwards. And as of right now, its acceleration is equal to gravitational force going downwards. So as soon as it starts to compress, the velocity is going to decrease and our acceleration is now going to be going in the opposite direction, so upwards. And same here, continues to compress, acceleration still pointing upwards. And once it's reached its maximum compression, the velocity is now going to be equal to 0, but our acceleration is still going to be going upwards. For the expansion of the ball, we have it beginning to expand here. So now our velocity is going to be going upwards. And same with our acceleration now. It's in the same direction as the velocity, so it's going to stay in the upwards direction, upwards, upwards. And just before it accelerates off the ground, we see the velocity and the acceleration are both going upwards. So for part B here, we need to draw a picture of the ball in contact with the floor and identify the forces. So when it's touching the floor, we have gravitational force, which is pulling it downwards in a perpendicular direction, and we have the normal force, which is pushing upwards in a perpendicular direction, or perpendicular to the ground. So for part C, I'm going to draw a free body diagram, and we want to draw our normal force longer than our gravitational force. So there's a stronger normal force than there is a gravitational force because we know that our ball is accelerating in an upward direction, so our net force has to be going in the positive y direction. So here's our net force, which we show is in the positive direction. And to explain this in words, we can say that when the ball is in free fall, we know its velocity is going downwards along with its acceleration. As soon as the ball reaches the ground, begins to decompress, its velocity is decreasing and the acceleration is now going in the upwards direction, opposite to the direction of velocity. Because the acceleration is always going upwards when the ball is on the ground, the normal force is greater than the weight, and it forces the ball back up into the air. So that's why it doesn't just stay on the ground, it goes back up into the air. And this problem relates to what we're learning in chapters 5 and 6 about Newton's first and second law. And it reinforces our learning goals for this week of identifying forces acting on an object, drawing an accurate free body diagram, and explaining an observation on the basis of physical principles.